Okay, thanks for coming. So today we have Xiaofan Yuan, new member of EcoPro. She's going to talk about rainbow things. Okay? Please.
Thank you very much for having me giving a talk here, and also thank you very much for having me with a job here. So I'm going to talk about rainbow structures in edge-colored graphs. This is joint work with Andrzej Czygrinow, my postdoc mentor at ASU. So let me start a little bit about the area of the extremal graph theory. Probably it's a little bit too trivial for the audience, so I'm going to go a little bit quick on this part. But if you have any questions or anything needs to be clarified, feel free to interrupt me anytime. So extremal graph theory studies quantitative connections between various graph properties, both global ones, such as the number of vertices, number of edges, and also local ones, such as if there's a triangle or so. And problems in this area can often be formulated as optimization problems. How big or how small a parameter of a graph can be, given some constraints. For example, this is well known for more than 100 years. How many edges can there be in an n-vertex graph such that there is no triangle? Mantel answered it in 1907 that the maximum number of edges in a graph on n vertices with triangle is a quarter to n squared. And we all know that an extremal graph would just be a complete bipartite graph, balanced. And this field is also closely related to other fields such as theoretical computer science and additive combinatorics. So for example, Ruza and Simaredi gave an extremal graph theory proof of the Ross theorem, which sounds more number theory. It states that if A is a subset of numbers from 1 to n, and if there's no three-term arithmetic progression in A, meaning that there's no x, x plus d, x plus 2d, where d is non-zero, then the size of A has to be little o of n. Okay. And how they prove that? It's based on the regularity method. Roughly speaking, Simaredi's graph regularity lemma states that the vertex set of every graph can be partitioned into a bounded number of parts, so that between each two parts, up to some epsilon parts, we don't care. Between most of the parts, the graph behaves quite similar to random graph to some extent, so that we can use the good properties in the random graph setting. And roughly speaking, they prove it in, one proof can be stated in the following way. Based on the regularity method, one can show that if there are fewer than delta n cubed triangles in the graph, then the graph can be made triangle-free by removing fewer than epsilon n squared edges. And this gives us a direct corollary called the diamond-free lemma. A diamond is a graph like this, where we have one edge, which is in two triangles. So diamond-free means that in the graph, every edge lies in a unique triangle. Okay. Then the graph has little o n squared edges. And they can prove Ross theorem pretty much using this accelerate graph, defining a graph by the elements of A and add edges between x, y if the difference is in A, and the other one, if the difference is in A, then the last one if half of the difference is in A. Then non-trivial, any three-term AP in A give us a triangle in this accelerate graph. Well, each edge would be in a trivial triangle, meaning that x can show up in A and xxx could be a trivial three-term AP. And so this is a taste of this area. What we are working on is under the set of of edge-colored graphs. And the parameter we considered is the color degrees. More precisely, an edge-colored graph is a pair GC, where G is a graph defined on vertex set V, edge set E, and we have a color mapping C maps from the edge set to a color set, which gives a color to each edge. And we use this DCV to denote the number of colors on the edge set, on the edges incident to V. So in other words, V sees all the colors on the incident edges, then DCV is the number of colors V sees. And we use delta C to denote the minimum among all the color degrees in the graph. And we say a subgraph is a rainbow subgraph if all the edges receive distinct colors. Okay, so for example, this is a rainbow set of chalks.
Okay.
So each color show up at most one time. GC is called a K-rainbow, is called K-rainbow connected. If between any two distinct vertices, we can find K internally disjoint passes such that the entire graph, the entire subgraph induced by those passes is rainbow. In particular, if it's one rainbow, we say it's rainbow connected. If it's one rainbow connected, we just say it's rainbow connected. Okay. And a general question in this setup can be stated in this way. For a property T and a number n, determine the least delta in terms of nt such that if an edge-colored graph G of order n satisfies the minimum color degrees at least delta, then G has property T. And there are a variety of previous work in the setup. So for example, if property is the existence of a rainbow triangle, then Li showed in 2013 that if delta is half of n plus 1, then there will be a rainbow triangle. And indeed, this coincides with Mantle's theorem. So as long as the degree assures a triangle, then the color degree assures a rainbow triangle. However, naturally, one might ask, is it always the Turan bound? In fact, it's going to be very different in the bipartite cases. So when T is the existence of a rainbow cycle plus 4, Czygrinow, Molan, Nagel, and Eusler proved in 2021 that the minimum color degree we need is roughly 1/3 of it. Recall that for general simple graphs, the Turan bound for the existence of a full cycle is roughly, the degree is roughly square root of it. Here we indeed need linear. Actually, I can give a quick rough argument on why you need that many. So if we consider a blow up of a directed triangle, we have n vertices, roughly this is 1/3 of n, 1/3 of n, 1/3 of n. And all the edges go in this direction. Okay. And this is clockwise direction. Then also now we consider a canonical coloring that we give each vertex, say this is vertex V, a color called CV. And then we color all the edges pointing to V in the color CV. All edges pointing to V are colored in the color CV. Then in this graph, what is the color degree? Because of symmetry, we can just look at one vertex here, for example. Okay, it has all the in edges from set A. All of them are in color CU, so they all receive the same color. And we also have all the odd edges pointing to C. Each of them receive a distinct color, CV1, CV2, da, da, da. So the color degree of U is going to be 1, which is CU plus 1/3 of N, which is all the odd edges pointing out from U. So in this graph, the color degree is indeed roughly 1/3 of N. Now I'm going to argue that there cannot be a rainbow C4. Okay. So if we wrap around, then all the lengths has to be multiple of 3. It's not going to work. So all the C4s would happen between 2 parts. Okay. It's going to look like this. In this directed graph, it's going to be something like this. So now, if we just look at those 2 directed edges, they both point to the same vertex, and there has to be a color confliction. And actually, this type of relation between the directed graph and edge-colored graph is canonical in this type of problems. So firstly, we are interested in the case when T is the property of the graph being rainbow connected. Now forget about the cycles for now, and let's focusing on paths between a pair of vertices in the graph. To state some previous results, we need to define that a graph is properly connected. We say 2 vertices are properly connected if there is a properly colored UV path. This is a weaker requirement than rainbow connected. And we say the graph is properly connected if between each pair of vertices there is a properly colored path. Okay. Then Fujita and Magnant proved in 2011 that if GC is an edge-colored graph of order at least 3, and if the minimum color degree is at least half of N, then G is properly connected. Actually, this is tight. One thing is, okay, so there are actually 2 extremal graphs. One is the trivial one if we have 2 connected components. Okay. Then if the graph itself is not connected, then it's not whatever connected anyway. However, this is not the only extremal graph. On the other hand, if we add an additional assumption that the graph G is connected, nothing is going to change. We can consider, so in this graph, on n vertices, we firstly keep 2 vertices x and y outside. And on the remaining n-2 vertices, I'm going to draw a regular tournament. Okay. So suppose n-2 is an odd number, then, so if this is vertex V, regular tournament means that there are half of the remaining vertices pointing to V, and with a similar, and then half of the vertices pointing out of V. Sorry, half of edges pointing out. Okay. And I'm going to give a similar coloring on this directed graph again. All the edges pointing into V are colored in CV, and all the edges pointing out receive distinct colors. And we do the same thing on the entire regular tournament. Then for X and Y, we just draw all the edges pointing from them to this tournament. So X has all the edges pointing to the tournament. Similarly, Y has all the edges pointing to the tournament. So this is almost a regular tournament, but two special vertices who has all the edges pointing to all the other edges, all the other vertices. Any questions about the structure? So this part is a regular tournament on n-2 vertices, and we still use the similar coloring method. Those are just two vertices pointing to this.
What's the coloring method for the edges incident on X and Y? The outside vertices.
Still, so if it's point to vertex V, it receives color CV. If it point to vertex U, it receives color CU.
So is X adjacent to everybody else?
Yes. So this is pretty much a complete graph. The underlying graph is pretty much a complete graph except for this edge.
So I didn't know. So this is, so you're constructing
Example to show that actually this is tight.
So the regular tournament is like before adding X and Y, right?
Yes, before.
Okay.
Any other questions? Okay, so now in this graph, what is the minimum color degree? By symmetry again, we can consider there are two types of vertices, outside vertex and tournament vertex. If we look at tournament vertex, say this vertex V, how many edges or how many colors it sees? Yeah, roughly half of it. So here we have one color, C of V, and here, in total there are n-2 vertices. Minus V, there are n-3 vertices left. So it's gonna be half of n-3. So this is exactly half of n-1. And actually X and Y, both of them see all the n-2 colors at all the n-2 vertices in the tournament. So they have bigger color degree. However, now if we look at a path, doesn't have to be directed path, just a path between X and Y. Since all the edges are pointing out from X, all the edges are pointing out from Y. So if we look at a path between X, Y, there has to be a conflict in the middle. At least one.
I see.
And quite similarly, whenever there is a conflict in the directed path, there is a conflict in the coloring. So this example shows that even if we already have minimum color degree half of n-1, and assuming the graph is connected, in fact, the underlying graph is pretty much complete, then it's still not enough. So this half of n is tight. And further, later on, Chen, Kanao, and Wang proved that with the same condition, actually the graph contains a properly colored spanning tree. Oh, sorry. Actually, this is a description of this example again, and just gonna skip this. And we proved that with the same assumption, actually we can show the graph is not only proper coloring but also connected, but also rainbow connected. More precisely, we show that if, but we can only do it for sufficiently large graphs. So more precisely, we show that there exists a integer n naught such that for every n, at least n naught, if the edge-colored graph GC of order n has minimum color degree at least half of n, then any two distinct vertices are connected by a rainbow path, and moreover is connected by a rainbow path of length 9. So one thing that the degree condition is tight, we can argue with the same counterexample. And also here we can show that between any two vertices, there is a path of constant length. So we are not sure if this line is optimal or not, but since it's a constant number, inductively we can find a bunch of good structures in the graph as well.
By constant length, you mean there's some constant that any pair of
Yeah.
vertices are joined by exactly like
No.
that constant length?
Yeah, so any pair of vertices are joined by a rainbow path of length at most 9.
Yeah, but like this constant is like if it's 8, then can I join every path by length 8 paths?
That's a very good point. We are not sure about that.
Uh-huh.
Sorry, what's your question?
So
This constant is universal. Every path has same length, or
You're saying instead of at most 8 or at most 9,
Yeah, yeah.
you want X.
There's a constant upper bound, not everything the same, right?
yeah, that's an upper bound.
Oh, yeah, the constant upper bound.
And yeah, so I think two understandings. One is that this is an upper bound. We're not saying that we can find same lengths between two vertices. And another thing is we're not sure if this line is optimal or not.
Mhm.
Okay. And
I'm sorry, can I ask a stupid question? Can you go back again? In the theorem, if I forget about rainbowness, if the degree of if every vertex has degree at least half, n by 2, sorry, then is there a bound on the length of the shortest path between two vertices without the colors?
So
Two, maybe?
yeah, so yeah.
Or
So
is it common number?
X sees more than half of the remaining
I see.
vertices. Y sees more than half of the
Sorry,
remaining.
Yeah, yeah.
But if I just tweak it a bit, let's say if I say it's at least n by 2 minus 1 or minus 2, then is it
Sorry.
Like 3 or something.
okay?
Yeah.
Did you assuming on the graph being connected already?
Yeah.
Oh, I see. So connected.
Yeah.
Oh, yes.
Yeah.
Maybe we do not need it connected because it is at least half.
Yeah,
of that.
here we don't. But so she's asking, what if we loosen this a little bit, move it to say half of n minus 1 or half of n minus 2? That's a great question. Any other questions or comments? Here, since we can manage to make it a constant length, with a inductional argument, we can show that actually, as long as we add a little bit of tail to the color degree, then we can get other structures. So if the minimum color degree is at least half of n plus 13 times k minus 1, then the graph is rainbow k connected. And actually, if we add 1k more to this color degree, then this graph is rainbow k linked. And if we give it some coefficient times k12, then we can assure that there is a rainbow subdivision of KK in this graph. Okay.
What are the killings?
That's a good question. I didn't define it here, so we know like, let me just say the difference between two connected and two linked. Okay. Now, if we fix 4 vertices, A, B, C, D, then if I say this graph is two connected, then I know that there has to be 2 different paths from A, B to C, D. It could go this way, or it could go this way. But if the graph is too linked, then we can actually make sure that, so if the graph is too linked, then we know that there has to be a path, 2 different paths from A, B to C, D, such that one goes from A to C, one goes from B to D. Okay. And
No matter which one is C and which one is D, right?
sorry?
No matter which one is C and which one is D.
Yeah, you make the choice. So I can give it's some
It's
intuition.
just like a complete bipartite graph. Something like that.
Complete bipartite
You
graph
can
has very
decide
high link.
all the vertices on the other side, which one link to which one.
Yeah, so complete bipartite graph has high linkage, high connectivity. The difference between them, we can see one example. Suppose we have a planar graph. Suppose we have the map of Dejiang. Okay. Then I claim that if this is an outer cycle of a planar graph, A, B, C, D, okay, assume this graph is too connected, then it's not going to be too linked. You can't find paths, independent paths from A to D as well as independent paths from B to C. Because on the plane, if I draw a path from A to D, it's already cut the surface into 2 halves. I cannot find a path going from B to C anyway. So if we are looking for a specific graph structure, then linkage is a much stronger requirement than connectivity. Sorry, does it answer your question? Any other questions or comments? Okay, so now I'm going to give probably the only proof in this talk. How can we see corollary 1 from our theorem?
So is the k squared optimal, this low order term?
Not sure. But you can see why we need it from my proof of the first one. So this is just going to be like
This
some
sort of mirrors the
Sorry?
extremal problem. When you have k
Correct.
squared
Right.
average degree, you have kk as subdivision.
Do you have k squared?
Yeah.
So it might be the case that you need k squared there. If you have k to the 1.99, maybe it's not enough.
Yeah, that's a very good point. I need to think a little bit, and I might answer your question after this talk. But that's a good point because I can tell you for say atom number 1, we do need at least linear of k. We do need at least half of n plus k. Then
So then I can ask the same question for all the sparse graph embedding. For example, it's known that if you have, let's say, 100k average degree, then you have k consecutive even cycle lengths, say, forming an arithmetic progression of times k. Okay, even cycle. Then is it true that if your color minimum degree is at least n half, every time I plus an n half there, plus 100k, can you get 100 rainbow even cycle forming a whose length forming an arithmetic progression? You know what I mean? So for all the extremal problem, is it true that I see a pattern here?
Yeah.
The mother's result saying that if you have minimum degree 4k, you can find no. If you have minimum degree 100k, you can find k-linked subgraph here you just add n number 2, you get rainbow
So
painting.
far it's same order.
I see.
Anyway, let's see the proof
Yeah.
of the first one.
I'll get back to the question
yeah.
maybe tomorrow.
Yeah.
Okay. So for further one, from the theorem we know that. Okay. Sorry. Now if we want to find k rainbow paths between vertices x and y. Okay. Now there are n vertices in the graph. From our theorem, there is a path of length at most 9 here.
Ah.
I'm just going to remove all the colors in the edges showing up here. Since the length is at most 9, I'm going to remove 9 colors in the entire graph. All the edges in those 9 colors disappear now. And also, there are at most 8 internal vertices. So say there are D, F vertices. Okay. Then I'm also going to remove all those F vertices. Okay. And after removing those 9 colors and F vertices, okay, now each vertex V sees all the original colors removing 9 colors, removing those F colors. Okay. So now the new DCV equals the original DCV minus 9 minus F. And also the total number of this graph is reduced by F. So from the half of n, we have half of F gain. Sorry, so let me do it again. So remove those 9 colors and also those F vertices. Now in the new graph, there are n minus F vertices. And if we look at arbitrary vertex V, then the new degree is going to be at least the original degree, which is half of n plus 13 k minus 1, okay, and minus 9 minus f. But the new n becomes n minus f. So I can rewrite this half of n as half of n minus f plus half of f. So I can rewrite it as half of n minus f. Now half of the number of vertices in the graph plus 13 times number of iterations I want to do minus 9 minus half of f. Okay. There's already 1/2 moving to this half of n part. So what I did is that when I remove a rainbow path between x and y, now in the entire graph, I ignore all the vertices already used and all the colors already used. In the new graph, every vertex still sees at least half of the number of vertices plus 13 times something minus, this is at most negative 13. So with deleting one path, the degree, roughly speaking, dropped by 13, at most 13.
I see.
And I'm going to remove the first n minus k path one by one, and I still have one path. So together we have k independent paths. Sorry, does it make sense?
I see.
And quite similarly for the k-linked, instead of removing those 8 vertices, I'm also going to throw away x and y. So one more needed. And here for the subdivision, I'm going to throw away roughly k choose 2 paths. So I'm going to need some k smart term. So this is some straightforward corollary. So from the method, I cannot tell you if this is optimal, but on the other hand, this might be correct, because if you look at this, so if we have 2 complete half of n plus a matching of yellow plus a matching of green, perfect matching, okay, plus k minus 2 perfect matchings, sorry, plus k minus 1 perfect matchings. Okay. Then I can further assume there are like all the edges in each component receive distinct colors. Then in this graph, the color degree is half of n minus 1 plus this k minus 2. Then I have half of n plus linear in k, actually maybe k minus 1 or something like that, color degree. But there cannot be k, well, the graph is not, we cannot find k paths such that all of them are in different colors. Because each of the paths has to use one color in the middle, and there are at most k minus 1 of them, k minus 2.
So that's the typeness example for which one?
For the swarm.
The first one.
Okay, so if let me make a little bit more precise. If I add k minus 1 perfect matchings in k minus 1 colors between them, then here each vertex sees half of n minus 1 color of edges plus this k minus 1, then it's still not enough. Any other questions or comments? Right. So, roughly speaking, we use the stability method for the proof, and if the graph is close to one of the extremal structures, actually one extremal structure is this regular tournament. Another extremal structure is this just 2 connected components. Then we can find such a path based on the structure. Otherwise, if the graph is not close to the extremal case, then we regularize it. Here, because all the outgoing edges, if we stay at one vertex, then all the outgoing edges, just in this example, they are in distinct colors. That means I'm going to have a lot of choice in the outgoing edges. So you'll see why very soon. So the double edges in this graph, I'm kind of combining the idea of directed graph and edge-colored graph now, but I'm going to firstly construct an accelerate directed graph based on the edge coloring. And then I'm going to store all the double edges in one graph, store all the other edges in another graph. I regularize both of them, and then I'm going to find a structure in the reduced graph. So now, how did I construct the accelerate graph? Firstly, recall that starting from a directed graph, we can give it an edge coloring using this idea. So to construct this auxiliary graph, we pretty much just go backwards. Okay, now if we look at one color, say alpha, then if we assume the original graph is minimal subject to this color degree, by minimal I mean, okay, so if there is a path, monochromatic path of length 3, then by removing the middle edge, none of the color degree is harmed. So at the very beginning, I can say my graph is minimal. In that sense, I'm not going to have any monochromatic path of length 3. So if I focus on one color alpha, then the structure would be a star forest, meaning that we could have isolated vertices, could have edges, path 2, or general big star. Okay. And now I'm going to define a directed graph as following. I go through every vertex V in the graph, focusing on color alpha. Okay. If this guy only see one edge in color alpha, I draw an edge pointing out corresponding to the alpha color edge. So this guy as well, so I'm going to have a double edge here. And you can see a double edge show up on this isolated edge. If it's isolated in alpha, it's gonna be very good in our rainbow path because there's no conflict anywhere. Okay. And here as well, this guy has a alpha edge, this guy has an alpha edge. Then this guy, it has two options. I just arbitrarily fix one option.
Oh, you want to make a transitive orientation?
Sorry.
So you're going.
So if this vertex V see one edge in color alpha, I just draw an edge pointing out from it. If it see multiple edge in color alpha, I just arbitrarily fix one edge and then draw an edge pointing out. So then after the entire process, I'm still going to have the structure, the property that V has distinct edges, distinct color edges going out. Only one edge in alpha, only one edge in beta, blah blah blah.
Oh, I see.
So if there are more choices, I ignore all but one.
So just keep one edge.
Yes.
For every vertex.
Yes. Yeah. So after the process, I'm still going to have the distinct outgoing edges. Except for one case. Say here, come back to our extremal structure, extremal example. This V is not going to have any outgoing edge in color CV because it's going to be messy. So when it corresponds to the case that's CV, see if this guy V sees many edges in color alpha, then that's a big center of color alpha. Okay. More precisely, we can say if it's at least square root of n, then in this case, I'm not going to draw any outgoing edge in color alpha at V. I just save this color alpha as C of V, as a candidate of C of V. And okay, I do this for all the colors. Now in this graph, if I look at a vertex, how many colors? What's the out degree of the vertex? When we go through all the colors, as long as it sees less than square root of n edges in the color, I added an edge in the color if it sees the color. Okay. Then this one is going to have out degree at least the color degree minus the cases when it becomes a big center at the color. By big, it sees half of n edges in that color, but in total it sees up to n edges. So it can show up as a center for at most square root of n times.
Wait, I can see this. If vertex V has degree less than n over 2 minus root n, then you have a no.
So,
No,
yeah.
I'm a bit confused.
Sorry, I mean, for color alpha we do this.
Yeah.
Then for color beta we do this as well.
Right.
After looking through all the edges, now fix this vertex V. Okay. For all the color it sees, I added one edge pointing out in the color, except for the case when we see, say, many edges in color beta. Then I don't add any out edge in color beta. That's the exceptions.
Oh.
Exception happens when there are square root of n edges. That means it happens for at most n over square root n
I see.
times.
I see. Okay.
Yeah. Maybe I should use n 1/3 and 2/3. It's probably better to understand, but it doesn't really matter. So the idea is that we save some candidate for C of V for some vertices. Any other comments? Okay. And also I mentioned that if I have a double edge, then it's easier to, it means that I don't have many conflict. It's probably good to use. So I'm going to store those double edges separately. I use G star from now on to store all the double edges. And also I have all the other edges which form an oriented graph. Let's call it D or D star. So actually after this auxiliary graph, I can precisely define the two extremal cases. One is saying that when I say is close to this case, that means I can separate the vertex set into two pretty much balanced sets, such that there are a very little portion of edges in between them. And in this case, we can show that there's a rainbow path of length at most 5 between each pair of vertices. And another extremal case is this pretty much a regular tournament. Regular tournament means that there aren't many double edges. And if we fix the color degree or alt degree to be half of n, no many double edges actually give you a almost tournament as well. Okay. So in this case, we say if the number of double edges is less than a small portion, then we can find a rainbow path of length at most 9. Actually, this is the only place we actually need 9 in our proof, and this is the most technical part. Okay. Otherwise, if it's not close to either of the extremal case, then I'm going to I'm going to use the regularity method. So you don't have to read everything here. Let's see. I can give a quick summary of the history or like the variations of regularity lemmas. The first several come from the original Simonelli regularity lemma, and then Alon Shapira gave a directed graph version. So, so pretty much you have all the edges going to one direction in a random behavior between two parts. And then later, I tried to find the history, but I wasn't able to find a very original one for this degree form. But there are a lot of versions of the degree form as well. For example, you can see a survey by Kuhn and Oskus. Roughly speaking, I remove some troublesome edges, and I move a small number of troublesome vertices to V0. Then I can make sure that I remove all the edges between the non-regular pairs, except for V0. And also I remove all the edges for the very low density pairs. And then I also make sure that at each vertex, I only remove up to a small portion of edges. So now this graph is regular, and furthermore, I can still use the degree bound up to some error term. So also I do a refinement for both the double edges and directed graph. Also the oriented part, removing double edges, a directed graph. Yeah, so we use this G star to denote the double edges. We use this R prime G to denote the reduced graph. We use D to denote the other edges, R prime D for the reduced graph of that. And then there is one more step we need to make, is that, okay, so D is an oriented graph, but the reduced graph doesn't have to be oriented, because there could be a regular pair such that there are many edges going this way. Also, there are many edges going this way as well. So it could be a regular pair for both directions. But in our application, I don't want the case, because those edges doesn't really perform as my real double edges. So last step is to, okay, so if there are two directions, I'm just going to keep one of the direction. More precisely, if ij and ji both show up in the reduced graph, then I include ij with the, so pretty much edit, so by the weight. If ij has greater density, then I add ij with its density divided by sum of the densities. Okay. With this adjustment, I can still make sure that the alt degree in this reduced graph, alt degree means alt edges plus double edges, is still roughly half of number of vertices minus error term. Okay. So with the structure of the reduced graph, we can show that there is always a rainbow path between each pair of vertices of length at most 8. So here we can get up to 8. And putting them together, we can show that, so case 1 at most 9, case 1 at most 5, case 2 at most 9, case 3 at most 8. Putting them together, we can show that there are always a path of length at most 9. So we don't know if we have same length of paths. Yeah, I think that's probably a very different problem. Now here, if two vertices are adjacent, we just don't care about them. Right. So that's about passes. And recall that I've mentioned about some existence of some cycles, and also because I put this in my abstract, I have to keep my words. So there's also previous work on the degree condition for the existence of even cycles. Because recall this example is quite different from the Turan-Bound. And okay, so we are also working on the case that if now we focus on bipartite edge colored graph, okay, and still focus on the parameter of color degree, then what is the threshold or what is the color degree needed for the existence of a cycle of length 2k? Okay. We can, in an ongoing manuscript, we can show that if the degree is, roughly speaking, a quarter to total number of vertices, then H contains a rainbow cycle of length 2k. And this bound is best possible. You can think wrapping up a directed blow up of 4 cycles, then it's roughly a quarter, but you can't get a cycle of length 6. Okay, so or for any odd k, then naturally for even k, say if we are looking for a cycle of length 4k, then the 4 blow up is not a counterexample or not an obstruction anymore. We can show that roughly 1/6 of the total number of vertices, we can find a cycle of length 4k.
Again, you use the regularity lemma?
Yes, yeah, so the method scheme is quite similar, but the details is very different. Okay, and this is also best possible. So you can thinking of wrapping up say blow up of 6 cycle, then you can get a cycle of length 8. Future directions. Question 1, the entire method based on regularity lemma, so it only worked for large enough n. And recall that in Fujita's results, they can actually show it for all n. So the first question is, does the whole thing work for arbitrary graph as well? We don't see any reason why it doesn't, but also if you want to show it for all n, then a very different method is going to be needed. Okay, question 2 and 3 are about the optimal constant and also the optimal function for the existence of, say, k paths. Also, could also be a subdivision of kk. Okay, we think it could also be of independent interest on the optimal function for the existence of a folder structure here as well. Okay. Thank you very much.
Thank you. Any questions?
Yeah, so your theorems really say things about digraphs, right? Because this color degree corresponds to minimum out degree, actually. So, I mean, is this really all just about digraphs? Like, it looks like your extremal examples come from digraphs.
That's a very good point. So the actually a lot of method for the non-extremal case coming from the ideas of the related work on digraphs, but then we still need to come back to the well, that's for the extremal case, but for the extremal case, we still need to come back to the colors at the end. Sometimes those like the edges we kept might not be enough, and we still need to look back to the color of the edges as well. That's a very good point. And let me make one more comment. So because it has a very close relation to the digraph problems, so those cycle questions could also has to do with the Kachata conjecture.
How do you connect vertices in the V0?
In
In V0, in the regularity partition.
how do I?
Present.
So you mean like in the color? So to find a path. Yeah,
pass.
that's a very good point. So actually, those vertices in V0 is gonna we need to take care of them differently. So there are always the exception sets, and actually to work on the vertices in the exception sets might need the longest length of the path. So even if it's in V0, then it still have a big degree. So we can firstly go from that vertex to a better vertex. Yeah, that's a very good point actually.
Yeah, that takes thing like you can find a rainbow cycle with very small size when k is very small constant, right? So it seems interesting if I get some flexible result, flexible condition on the middle degree, like 1/2 plus some epsilon times n. Then can you prove something like, okay, I can find a rainbow cycle factorization or decomposition? I mean, instead of just one rainbow cycle, is it possible? Even just a cover n minus little than vertices. Because I can give you some stronger assumption on the degree condition.
Factorization is a very global. Do you mean factorization for among all the vertices, or just
Vertex
a bunch,
disjoint small
100 disjoint
I
cycles?
want to find a lot of cycles. I don't even care about how large a cycle each could be, but I want all of them cover nearly all of the vertices.
Oh, I think that might be a very different question if you're looking for a decomposition structure. I'm not sure. But here, because everything we are working on are local. Because if we see so we always go from bad vertex to good vertices, and we ignore the other bad vertices. But if you are looking for a factorization, then
Maybe no factorization, but just cover. Final cover. Or small cardinality.
Yeah, because if you just remove one small cycle, your whole host graph basically.
yeah.
function at all.
So I'm saying if you are looking for 100 cycles, then you can just add 100 times the tail arrow term to get it. But if you are looking for a factorization, then I don't think this method work, or this method would work, because we always rely on a large n to find a small thing.
Oh.
So
Okay, any other questions? Okay, if not, let's thank the speaker.